Okay, it's on. So, hello everyone. Welcome again to our lectures on quantum field theory. So today we have Professor Nabil Iqbal, who will be lecturing on path integrals from quantum field theory. And he is a professor at Durham University, and he'll be guiding us through the different paths you take in quantum field theory, basically. And yeah, over to you, Nabil.
Okay, great. Thank you very much, Rakin, for that introduction. I think you can all hear me. So let me tell you what we're going to do today. Basically, I'm going to be with you for about 4 hours, 2 hours today, 2 hours tomorrow. Today, we're going to understand path integrals for quantum field theory. And tomorrow, we're going to understand gauge theories, okay? The truth is, each of these topics is huge, and I will not really be able to teach them properly in this time. And so I'm going to give you a bit of a flavor for what's happening. You can look at the notes that are online. They're already posted on the website. Those have more equations than I'm going to write down today. And you can look at those for more detail. Some derivations I will not do all the way. I'll just sort of give you the idea, and I'll leave it to you to fill in some of the gaps of those derivations. Okay? Okay, so let's get started. So I'm using the same notation as everyone else in this course so far. So in particular, I will sometimes write x, one second. I will sometimes write x mu, which includes a time component and a spatial component. Okay. And just like everyone else, I'm going to set h bar equal to c equal to 1. All right. And I'll put back the h bar a little bit sometimes, but I'll never take the c, put the c back. And finally, there's a homework problem that involves quantum statistical mechanics. And for that problem, KB, Boltzmann's constant from thermodynamics, is also 1. Okay. Okay. Now, this lecture is about path integrals. What are path integrals? All right. What is the point of path integrals? So path integrals are a completely different way of doing quantum physics. So let me just remind you, how did we do quantum physics up till now? What we did normally was we thought about operators. Okay, so we had some sort of an operator, okay, which phi hat, which depended on space and on time. And we sort of looked at different commutation relations of this operator, right? Like we looked at, I don't know, phi commutator with the Hamiltonian, and that's something. I chose a poor example because I don't remember exactly what you get, but you get something that you can calculate and so on. And so this business that involved a lot of commutators and operators is called canonical quantization. Okay? And it is, in a sense, the normal way of doing quantum mechanics. But by normal, I mean, this is what you learn first in your quantum mechanics course. You learn about operators and things like that. They act on states in the state space and all of this. Okay? Now, it turns out there is a completely different way of doing quantum mechanics and quantum field theory. And that different way is what we're going to study today. It's called path integrals. In many ways, it is more elegant, okay? It is very beautiful. And just like most things that are very beautiful in physics, if it's beautiful, it probably means you can use it in a useful way to calculate things. And I'll sort of show you some of that as we go, okay? So before doing path integrals for quantum field theory, I'm actually going to spend most of today doing path integrals, not for quantum field theory, but for quantum mechanics. So I'm going to show you how to calculate some things that you know in quantum mechanics from path integrals instead of from normal commutators. And then at the end, we will show how that stuff easily then transfers over to quantum field theory. Okay. Now, again, I'm doing everything quite fast, so I'm going to give you some references. There are lecture notes online that you can look at. Another thing is to look at the book by Anthony Z. Okay, it's called Quantum Field Theory in a Nutshell. And most of what I'm doing is sort of from the philosophy of his chapter 1. Okay, the very beginning of that quantum field theory book. And also there is a textbook by Peskin and Schroeder that I think everyone has probably heard of already. And you can look at chapter 9 of that textbook. That's the other one that I used to prepare these things. Okay, now, before getting into this, into math, I want to first motivate this. And I want to motivate this by talking about the double slit experiment. I think everyone here has heard of the double slit experiment, right? I actually can't see you, but I'm assuming that you're all nodding vigorously, looking at your screens. Everyone knows double slit experiment. So what is the double slit experiment? The double slit experiment looks something like this. We have a slit that has two holes in it, A1 and A2, okay? And there's some sort of an observer. Let's call that O. This is the observer. This is meant to be an I. Sorry, I messed that up badly. This is an I looking. And then there's a source over here, okay? And this source is creating light. Now, what the double slit experiment tells us is something like this. If you want to calculate the amplitude, which I'm going to call curly A, the amplitude that we observe something, that we observe a particle at O, what we do is we think about the two paths the particle can take, right? So for example, the particle could go like this, and then like this through this hole, all right? And that has some amplitude, which I'm going to write like this. S goes to A1, goes to O. Okay. There's another amplitude. The particle could go like this, in which case we then find A, S goes to A2, goes to O. Right? Everyone knows this. And in your first quantum mechanics class, probably you saw this sort of thing. The point is you add these two things together and then they usually oscillate in space. And then you get some sort of cosine or a sine. And this thing looks like, there's some cool thing happening here. People have seen this kind of thing, right? Okay. But I want to take a step back and just think about what this really means. The way to find the amplitude is by adding together two different things from here and from here. Okay? Okay. Now, let's do something else. Let's imagine that we also add another hole here, A3, okay? Then what is the amplitude? Well, the amplitude is that you go, oops, I messed that up. The amplitude is then that you can also go like this. And so we should add another term here, right? S goes to A3, goes to 0. Okay, and then we can imagine putting more holes, okay? And then obviously you just keep adding this up over all the holes. But now, we can imagine doing more crazy things, right? Like, imagine that we put another screen here, all right? And then we poke some more holes in that screen. Okay, then you can go like this and like that and like this and like this and like this and like this. You can go in all these different ways, right? You can go in all sorts of different ways. What if I put a hole here, a screen here, and then I put so many holes in the screen, I just puncture the screen completely with holes, so many holes that there's no screen at all. Then that means you should go like this and like this and like this and like that. This is basically, you should sum over all the different ways of getting from here to there, right? So what that means is, what is happening if you just think about empty space with no screens? You can imagine that you can just fill all of space with this, and then imagine that there are no screens at all. And what you should do is sum over all the possible ways for the particle to get from here to here. So the real claim is that this sum is actually equal to all the ways to go from S to O, okay? This is what the amplitude should be. And I see there's a message saying Feynman asked the professor about this. That is absolutely right. In the intro to Tony Z's book, you will see that supposedly Richard Feynman asked his professor about this, and the professor was like, oh, I don't know what to do, blah, blah, blah. And then Feynman went home, of course, and because he was Feynman, he actually invented the path integral formalism that we're going to use today. Okay. So now this is kind of nice, right? It sort of feels good. And the point is that if you want to make this into a calculational principle, we have to figure out how to add up all these paths, right? It's like some sort of a sum over all paths. But what does that mean really? Like, how do you take a sum over all paths? And also, what is it that I sum? It turns out it's a phase. But what is the phase? How do we calculate that phase? This is what we're going to do. We're going to figure out how to do that today. Okay. Okay. So let's now do it. That was motivation. And now we're going to actually do some math. Okay. Now, we're going to do today many integrals. So first, to warm up, we're going to do some practice integrals that everyone already knows, I think. Okay. So now, everyone keep in your mind this cool idea that we're summing over all paths at some point. And for now, we first do some basic integrals. Okay, this is a warm-up, basic integrals. Okay, and I'm doing this now because we're going to need them later. So first of all, there is such a thing. There are actually very few integrals that we can do in closed form, but one of them is the Gaussian integral. Okay, so here I'm integrating x over the real line of e to the minus a x squared over 2. Okay, and now this is an integral that people can do. It is known how to do this integral. If you don't remember, you can look it up on Wikipedia. And the answer is this: square root of 2 pi over a. Okay, this is a single Gaussian integral. Is everyone happy with this single Gaussian integral? If you are not, say so in the chat now. Okay. Okay. Now let's do something a little bit fancier. Let's imagine a single Gaussian integral with a small shift in the action. So instead of minus ax squared, I'm going to do minus ax squared minus jx. Okay. Quadrice linear. And this turns out to be 2 pi over a e to the j squared over 2a. Okay. So this j multiplies x linearly, and it turns out you get a j squared here divided by 2a. Okay. So this is a shifted Gaussian integral. And if you do not know how to do this, it is a good exercise to just go from here to here. You can do this by completing the square in the exponent. Okay. Okay. Now that is one variable. Today we are going to do ultimately infinitely many integrals. So to warm up, let us do an integral of a small number of finitely small number of variables. In other words, let's do an integral over Rn. Okay, so consider xi, which has components x1, x2, blah, 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 all the way up to xn. And now let's do this integral. I'm going to call it I. I equals to the integral over all of the components. Okay, so this is just an integral over Rn. So dx1, dx2, dx3, dx4 of exponential of xi, aij, xj divided by 2, and there's a minus sign here, so it's almost left out. Okay, so in this formula, I'm using the Einstein summation convention, which means that I am summing over I and j, but I'm not writing that down. Okay, so A here is an n by n matrix. Okay, so you see that this is the multi-dimensional generalization of this integral here, right? Here we have xi, aij, xj, and here we have minus ax squared. This is the multi-dimensional version of this. Instead of one little a, we have n squared small, large a's. Okay, a matrix is worth. Okay, and now we have to do this integral. So have people done this integral in their lives before? Has anyone done this integral? Again, I can't really see you, but I'm assuming some of you are saying, no, no, we haven't. And some of you have done it. Yes, some of you have done it. Excellent. Okay. If you have not done it, that's okay. This is a homework problem in this week's homework. So you have to do it for your homework anyway. I'm going to tell you the answer. The answer is 2 pi to the n over 2 divided by the square root of the determinant of a. Okay. This is the determinant of this a here. All right. A is a matrix, so you can take its determinant. This is the answer to that integral. It's very nice, right? It's very pretty. It involves a determinant. The way to do this is to take this matrix and diagonalize the matrix. Okay. So you diagonalize the matrix A. In physics, we can always diagonalize every matrix. And even in math, A is symmetric, it turns out. So you can always diagonalize it. And then you work in each, treat each of the eigenvalues as an independent Gaussian integral. And then you get the product of the eigenvalues, and the determinant is the product of the eigenvalues. That's the idea. All right. But everyone should check this and do this at home for the homework. And finally, we need one more integral. Okay. And that's what I'm going to call I of j. All right. And that integral is the following thing. I goes from 1 to n. dxi. And again, this is very similar to the one we just did, or the one I just told you the answer of. But now I have a linear shift in I here. So here J is a vector in Rn. Okay, it has components R1, R2, R3, blah, 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 blah. Okay. And then we have that over here. And then this integral turns out to be 2 pi to the n over 2 divided by the square root of the determinant of A times the exponential of plus 1/2 ji A inverse ij jj. Okay. Let's just take a second and think about this again. What's happening here? You see, A is a matrix, and so it has an inverse, hopefully. And this is saying take the inverse of the matrix A, okay, and then dot it into J in this way. Ji dotted into A inverse, dotted into J. So in a vector notation, this would look like J dot into A inverse dot J. That's what's happening here. All right. And again, just to go back a little bit, this is the multi-dimensional version of this thing. Remember before we had J squared divided by little a, where little a was a number. Now we have capital J square, but you can't divide by a matrix. We take the inverse instead. Okay. So this integral, this I of J, will turn out to be very important. Okay, we're going to use this. And so the truth is, this is the homework problem, actually, not their other one. So after you prove this, you prove this one. Everyone go home and do that. We're going to use it today without proof, but I'm confident you can all prove this. Okay. Some questions now. This is a real integral. Should it not be absolute value of det A in the denominator? Good question. The truth is, this is a real integral. However, this integral only works if all of the eigenvalues of A, you see A is symmetric. I think that means that if A is real symmetric, I think that might mean that all of the eigenvalues are real. And then if any of them are negatives, it doesn't work anymore. So there's a quiet assumption about all the eigenvalues of A being positive. And that means that the absolute value is not needed. Okay. It turns out the phase of det A is indeed a very, very important thing in many areas of physics, which I'm not going to tell you about, but ask me in the Slack and I can explain to you why the phase of det A is so important. Okay. And a question about J, isn't J called the Hubbard-Satonovich field? No, this J isn't. Other J's are, but this J, to give it a name, call J the source. And I'll explain why it's called the source later. Okay. Okay, good. Now we are warmed up, and now let us derive the path integral for quantum mechanics. So we're going to derive the path integral in quantum mechanics. Okay. So right now we're doing quantum mechanics. And so I want you to imagine one quantum mechanical particle. Okay, here's my particle. And it has a position operator and, oh my God. It has a position operator and it has a momentum operator. I'm going to call them Q and P. Okay. And so Q is the position, P is the momentum. And I'm going to give this guy a Hamiltonian. And Hamiltonian will just be the normal sort of Hamiltonian that you know and love. P squared divided by 2m plus V of Q. Okay. So this is some sort of potential. And this is the kinetic energy term in the Hamiltonian. So this is really normal quantum mechanics from the previous things. Okay. Okay. So now we have H is P squared over 2m plus V of Q. And for now, the truth is I'm going to set V to 0 in a little bit, so I'm not going to tell you any more about it, but let's keep it arbitrary for as far as we can go. And now I want to calculate something in this. I want to calculate a formula for the following object. I want to calculate a formula. So the goal of this part is going to be to calculate the following thing. I want to calculate the inner product QB e to the minus IHT times QA. Okay. Let me just take a second and talk about the hats. I'm going to put a hat on every operator. So every operator in the quantum mechanical Hilbert space has a hat on it. So there's a hat over here. Okay. Now this is telling us the probability to go from QA to QB in time t, right? This is saying start at some point QA, evolve with the Hamiltonian, and then the particle does some crazy thing, and then measure it. If this is QA, then measure it at QB. Okay, that is what this quantity is measuring. All right. Now, the truth is, everyone knows how to calculate. Oh, sorry, so one more technical thing. These Qs are position eigenstates. So what that means is, so QA is a position eigenstate, which means that Q hat of QA equals to QA times QA. All right. So what that means is, this is an eigenstate of the operator for position. QA is a number, acting with Q hat brings down that number. Okay. So QA and QB are the same like this, and they are position eigenstates. Okay. So now what I want to do is I want to derive a formula for this using some fancy new techniques. Everyone knows how to calculate this, right? You can just, use your normal quantum mechanics class, write down the Hamiltonian, take the exponential, blah, blah, blah. But I want to find a cool formula for this. So the first thing that I'm going to do to find a cool formula for this is I have my time interval t. Okay, so I'm going to start drawing my time interval here like this. So here's my time interval t. Okay, I'm going to take this time interval and split it up into many small chunks. Okay, so each of these chunks has a width epsilon. So I'm going to split t into small chunks. Okay, and each chunk has size epsilon. So in particular, if we call n divided by t over epsilon, n is the number of chunks that I have altogether. There are n little chunks here. And now I can write my Hamiltonian as e to the I h hat t equal to e to the minus I h hat epsilon, e to the minus I h hat epsilon, blah, 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 all the way to the end, e to the minus I h hat epsilon. And there are n factors of e to the minus I h hat epsilon here. Okay. Okay. Is everyone with me so far? Let's take a second to pause what we just did. We have taken this time interval, split it into many chunks, and now we're evolving each of these little bits with an e to the minus I h epsilon. Okay. That is what we're doing. Okay. I'll just let everyone take a second to catch their breath. And there's a question. So there's a more general question. Del, if it's okay, I'm going to handle that question in the break because it's a bit more general. Are there any technical questions about what we're doing right now before I continue? Okay, great. Next, the next amazingly clever thing that we're going to do is in between each of the small epsilon pieces. So in between each of these chunks, in between each of these pieces here, this is a clever trick. I am going to insert a complete set of states. In other words, I'm going to write the identity 1 as an integral over dq sub k, q sub k, q sub k. Okay. So we can always do this for any set of eigenstates of any Hermitian operator. You can always decompose the identity as an integral over this complete set of states. And now this k refers to which of these guys I'm doing it in. So for example, this is going to be kn, this is kn minus 1, and so on. Okay. So I'm going to insert one of these guys inside every chunk here. So what does that look like then? The formulas now are going to start to become a little bit long. All right. So let me call the starting point. So this is okay. So now just become a bit long. I apologize, but it's not conceptually long. It's just long on the board. This is what I'm trying to calculate. And now this is equal to QB e to the minus I h hat epsilon, e to the minus I h hat epsilon, blah, blah, blah. Hat epsilon QA. And now I insert all these sets of states. So what does that look like? I have QB e to the minus I h hat epsilon integral dqn qn minus 1 qn minus 1. So that one I put right in here. Okay, I inserted 1. And now I keep going. E to the minus I h hat epsilon. And now I put another one here. dqn minus 2. qn minus 2. qn minus 2. Blah, 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 blah. Okay. And then I do that in each of these things, okay? Into each of these little chunks, I do that. So I end up with about n of them. Right? And finally, at the very end of this thing, I get a piece that looks like this, Q1 e to the minus I h at epsilon QA. And this is where the whole thing ends. This QA is this QA here. Okay, so this is actually great progress. So let me explain why this is great progress. It's great progress because though I now have a very complicated looking integral, each thing appearing here is actually quite simple. They all take the form of e to the minus I h hat epsilon in between two position eigenstates. Okay, so the thing we need to figure out q to the k plus 1 e to the I h hat epsilon q to the k. Okay, this is the basic structure that appears over and over again. Okay, so for example, it appears here. We have q e to the ih. We have q e to the ih, you get the idea. So if we can figure out how to evaluate this, then we can stick that back inside and then just take many, many products of it. Okay. Now, let me just tell you physically what we're doing. Physically, what we did here was we've introduced many integrals over Q everywhere here. Okay. So we're doing like one integral here, one integral here, one integral here, one integral here. And now each integral means that we are sort of asking, what can the particle do? And by integrating each of these things separately at each point in time, we're really basically approximating the set of all possible paths, but by discretizing the path distance, okay? So that's what's happening, but at the moment we're just doing some math, so we don't need to think about that. We can just do some math and calculate, okay? Okay, so now you have to calculate this. And now, notice, by the way, in this notation, it makes sense to call this QB. Let's just call QB equal to Q sub n and call Q sub A equal to Q sub naught, because then this notation makes a lot of sense. Then we're going from Q1 to Q naught and from Qn to Qn minus 1. Then that fits nicely with this notation here. Okay. Okay. So now we're going to calculate this. And now to make my life easier, I'm going to assume that the Hamiltonian H equals to P squared over 2m. Okay. In other words, it's a free particle. There's no potential. You don't need to assume that. Okay. In fact, I'm going to encourage you to put the potential back and see what happens. But again, for the interest of time, I'm going to assume this and go on. Okay. It'll save like 5-10 minutes. So what that means is I want to calculate the following thing. I want to calculate Q sub k plus 1 e to the minus I p hat squared over 2m qk. Oops, epsilon. Okay. Okay. So now we need to do this calculation. And this is really just a basic quantum mechanics calculation. Let me remind you how to do this. So this is the momentum and this is the position. So they don't commute. But what is the inner product of these two operators? So if I have a position eigenstate and a momentum eigenstate, their inner product is e to the I times qp. Is this equation familiar to everyone? Why this is this equation? Why this looks like this? What this is saying is that a momentum eigenstate is a plane wave. And you know that, right? Like particles, plane momentum eigenstates, momentum states propagate a lot. That's a plane wave. Okay. So that's what this equation is saying right here. And we're also going to need the completeness relation in momentum space. And that equation looks like this in my normalization. Okay. Where again, these P's are momentum eigenstates. Okay. And because it's a momentum eigenstate, what that means is that if you act on this P with the P operator, you just get the number P back again. That's what it means to be a momentum eigenstate. Okay. So now let's calculate this. So starting from here, my iPad is not cooperating. Okay, I'll write that down again. So starting from here, we have integral dp divided by 2 pi q to the q sub k plus 1 e to the minus I p hat squared over 2m epsilon. That's an epsilon. And now I'm inserting this complete set of states here. And then there's a QP here. So I've inserted a complete set of states here. Okay. And that's this complete set of states here. Okay, great. Now, what is this? This quantity here is e to the minus IPQK. Okay. What is this quantity here? Because this is a momentum eigenstate, we can just operate with this on that and just get e to the IP squared divided by 2m, the number. Okay. And once we have the number, we can pull that through here and take the inner product of qk plus 1 with p. And so once the dust settles, what we get is just integral dp divided by 2 pi e to the minus I p hat squared. Oops, not a p hat anymore, just a p squared divided by 2m epsilon. And then there's this inner product and then this inner product. And so we get e to the IP qk minus 1 minus qk. Okay, this is equal to this. Okay, let's take a second and stare at that formula for a second. This is nice, right? We had something complicated, some sort of, inner product in Hilbert space between different things, between this and this operator. This, though, is just a number, right? It's just an integral over a single variable p, okay, with some numbers in here, q sub k minus 1, and a p squared. In fact, it's a very nice integral because it's an integral of e to the minus p squared. And so this is actually a Gaussian integral. And in fact, we know how to do this Gaussian integral because I wrote it on the board when I started this. I remember I told you we need to do this Gaussian integrals. This is a Gaussian integral. And if you then just look back in your notes at the Gaussian integral from like a little while ago, this one right here, you can use this result to just immediately do the integral over p. And what you find is that it is minus Im over 2 pi epsilon to the 1/2 times the exponential of im qk minus 1 minus qk squared divided by 2 epsilon. Did I choose a minus with a plus? Yeah, sorry. That's a plus. It's a plus. It does not matter at all, as you'll see. Okay. So we went from here to here by just doing the Gaussian integral. Okay. Okay. Now, let's see. So strangely, my battery is dying. So give me 1 second to find my charger, and then we will actually let me keep going, and then I'll take a small break for questions, and then we'll find the charger. Okay. Okay. So now we're almost done. Okay. Because this was one of the bits that made up the whole integral. And now we can put all of these bits back together. All right. This was one of the bits in this integral here. So now we can assemble all those bits back together. And what we find after that is that QB times e to the minus I h hat t times QA equals 2. So we had m of these little bits. So we assemble all these little bits in this way. We have n over 2 of them altogether, because we have a factor of n and the 1/2 over here. And then remember, we were doing a lot of integrals. Those integrals are still there. So we still have to integrate over q at each point along the way. And the thing that we integrate at each point along the way is e to the I m epsilon over 2 times the sum, k goes from 1 to n minus 1, of qk minus 1 minus qk over epsilon squared. Okay. So in other words, that is all of these products over and over and over again appearing in this thing. So let me just remind you again what we did, because it's been a bit of a long calculation. We had our time. We split time up into many chunks. Over each chunk, we inserted a complete set of states. So we had one product that looks like this in each of these little chunks. We took the product over all those together, and we got the final answer. And we're still doing one integral over q at each of these chunks. Okay, that's what we're doing. Okay, and now we're almost done. The final thing we're going to do is take the limit that epsilon goes to 0. Okay, because remember, epsilon is meant to be very small. Let's take it all the way to 0. So what is happening, actually, if we take the limit where epsilon goes to 0? Some of these things should look really interesting here. The limit as you take epsilon goes to 0 of qk plus 1 minus qk, in other words, this thing right here, as you take this limit, that limit is equal to q dot, right? Because I'm taking q here, subtracting q here, and then dividing by the distance between them. That is exactly dq dt. It's the definition of the derivative, right? And similarly, if you look at this guy here, this sum over epsilon, this sum over this limit as epsilon goes to 0, sum over epsilon is exactly the integral dt, right? So if we now recognize this, we recognize that this is dq dt squared, and this sum over many, many small strips, all with weight epsilon, is like the integral dt, then we recognize that this, now we can write the truly, really, really beautiful expression that the inner product going from QA to QB is equal to the integral over all paths of the exponential integral I from 0 to t dt q dot squared. Right. Okay. This is the formula for the path integral. This thing here means integrate over all paths, and the integral over all paths is formally defined in the following way. It is formally defined to be the integral dq is equal to the limit as n goes to infinity of basically everything that we had up there, minus im divided by 2 pi epsilon, divided by n over 2 times the integral, integrate over each of these positions, q to the n minus 1 dqk, with the restrictions that q of 0 equals to qa and q of t equals to qb. In other words, this is saying sum over all the paths going from QA to QB, sum over all of them, and for each path, evaluate integral of e to the I dt q dot squared, then sum all of those up, weighting each of them by the exponential of that integral. Okay? I'll let everyone stare at this while I try to save my laptop from dying. Okay. So everyone stare at this thing. Okay. I think I've rescued my laptop now. Okay. So this is the formula we have been trying to derive. Okay. Now, I think we're almost time for a break, but let me just say one more thing and then we'll take a brief break and then we'll keep going. So are there any questions actually at this point? How does everyone feel about this this formula? Does this make sense to everyone? Where did the m go in the exponential? Yeah, I think I just dropped it by accident. Sorry. Yeah, let's see. It's a good question. I think I just dropped it. Yeah, I'm sorry about that. Yeah, I just brutally dropped it. It's quite. Just make sure that's true. There's an M there. It's clearly gone after that. I think I just forgot it. Yeah. So because I'm a little bit nervous about where it went exactly, I'm going to say that now M is equal to 1 from now on, from here onwards. I'll try to put it back. I think it goes here. And then, I think it's just there. Yeah, never mind. M's not 1. I just dropped it in that formula. Yeah, that's right. Okay. Yeah, sorry. Thank you. Thank you about that. Yeah. Okay. And then there are some more questions. Why are we considering only time slicing and not both time slicing and space discretization, since particle path is evolving in time and space? That is a truly excellent question. And the point is that over here, time and space are quite different, okay? Because you see, we're doing normal quantum mechanics. Normal quantum mechanics is not Lorentz invariant. It doesn't know about the symmetry between time and space. And so time is how we sort of, evolve time is the operator that, what's the way to put this? Time is related to the thing conjugate to the Hamiltonian H, whereas space could have been discrete, but it's not in this thing. Space instead spans the Hilbert space of the particle. Okay, so one of them is the parameter that we use to evolve. The other spans the Hilbert space of the particle. Okay, I hope that helps answer that question. Why are we assuming we can slice the Hilbert space in this way? There's another question. There is no assumption here. The quantum mechanics of a particle is spanned by the set of particle eigenstates. That's the definition of quantum mechanics of a particle. So what you can ask is, say you had something that wasn't a simple particle, what would you use then? And that's really interesting, and we'll talk about it. Yeah, okay. Good. And let's see, there are more questions. Some are answering this. Okay, another excellent question. What about the convergence of this integral? This is a great question. This integral doesn't converge at all. Okay, it's like the worst convergent integral ever. And we're just gonna not worry about that and just live our life, and it'll be okay. All right. There's some places where it won't be okay, and we'll think about those carefully. But as physicists, we only worry about convergence if it means something physically. All right. So things will be infinite all the time. We just have to live with it. And you'll see that things do actually make sense. All right. Good. More questions. Don't I think that slicing the time would break the notion of background independence if one tries to unify GR with quantum mechanics? That's a really deep question. It's above the pay grades of this, but I'll say that the truth is that isn't the thing that breaks the background independence, actually. Yeah, that's not the thing that really causes the problems. Yeah. And finally, more questions. Is discretizing the spatial dimension X from the first lecture a sort of path integral? No, actually, that's just, again, the sort of thing we always do in this is we often discretize when we need to. And that was really just sort of making, it was a trick we did to make other things finite. It was not related to path integrals in any simple way. And finally, another question, if it's not convergent, can we renormalize the integral? There are many ways in which this integral is not convergent, okay? One of them has to do with the fact that, that we're taking the separation between time points to be very, very small, and the limit as epsilon goes to 0 is not actually convergent. You can kind of see that here, right? Look at this product. There's a product over n, and n goes to infinity. So this thing is like a hugely infinite number, okay? And we don't really need to renormalize that, but it's a good question, because things that have to do with short distance problems, like this delta t, this epsilon becoming small, is the kind of thing one has to deal with renormalization. It turns out in quantum mechanics, you don't have to use the machinery of renormalization, but in quantum field theory, you do. Okay, so your question is a very good one. And now there are other ways which is not convergent. So for example, notice that I'm doing an integral of e to the I times q squared. That's not a convergent Gaussian integral. That we'll deal with later explicitly. That actually means something important. Okay. Okay. But again, these are great questions, and you're sort of preempting what I'm about to say. Okay. Okay. So let me keep going a little bit, and then again, I'll pause for more questions and a short break as well. All right. Okay. So we have this beautiful formula. Okay. It's integral e to the I m q dot squared. Now, okay, that's fine. But now is a good time to imagine putting back the potential. Okay, so remember, we started with h hat equals to p squared over 2m. Okay, and now we should put back this v of q that we got rid of earlier. Okay, now I'm not actually going to do this calculus. I'm not going to do this calculation, but now what you can do is repeat the calculation with this v of q. It's really quite simple to do. I encourage everyone to do it. Repeat the calculation. And if you repeat that calculation, then the formula is modified to look like this. QB e to the minus I h hat t QA is equal to the integral dq exponential of I integral 0 t dt m q dot squared over 2. Thank you to the person who caught that. Minus v of q. Okay. This minus sign is crucial. Notice there's a plus sign here, and it becomes a minus sign here if you go through the calculation. Okay. This minus sign is important because what it means is that this quantity here, what is this quantity, everyone? Kinetic energy minus potential energy. What is that? Anyone? Yes. Happy to see the chat is exploding with the word Lagrangian. This is the Lagrangian of L, Q, and Q dot. Okay. And what that means is the quantity appearing here is the time integral of the Lagrangian. So the nicest way to write this is integral dq exponential of I S of Q. Okay, where S should be defined, should be thought of. This S is the action, and the definition of S of Q is the integral dt of the Lagrangian Q and Q dot, okay, over the path, right? So this S here is the action. So I think this is the nicest way to write this formula. So let me just repeat it here so I can emphasize the niceness of this formula. What this is saying is, to figure out the probability of going from QA to QB, what you should do is integrate over all paths, okay? Now remember, there are boundary conditions on the path, and what this is actually saying is integrate over all paths that start at QA and end at QB. So maybe I should put that in here explicitly. In this integral, it's a fact that Q of 0 equals to QA and Q of t equals to QB. This is a boundary condition on the paths in the integral. So you do an integral over all paths, and you weight each path by the exponential of the action evaluated along the path. Sum those all up, and you get the probability amplitude, okay, of going from QA to QB. This is the main formula of path integral quantum mechanics, okay? So this should feel really soothing, right? You know, like just looking at this formula, you should feel a bit at peace. It's such a nice formula. It's so cute. There's an action there. And also this might help you with something, a problem you might have had. You know, classical mechanics, classical physics, you can formulate it with an action with the Lagrangian or with the Hamiltonian, right? And you get the same answers either way. But you do quantum mechanics, you normally start with the Hamiltonian, you just work with that. You might have asked, what is the Lagrangian way of doing the quantum mechanics? This is the Lagrangian way of doing the quantum mechanics. Okay. Okay. So I think this is a good time for us to take a break. Okay. So we'll take a break for, let's say let's meet again. We'll take a break for 8 minutes. And so we'll start again at 5 minutes after 8 p.m. Bangladesh time. And that's 5 minutes after 3 p.m. UK time. So we'll reconvene then. And I'm here. Anyone wants to ask any questions? Any questions, anyone?
Okay,
Okay,
so I'll
there are
pause
some
the
questions.
recording for now.
Yeah, let's pause the recording. Yeah, that's right. Thanks. Okay, welcome back, everyone, after our extremely long 7-minute break. So let me remind you where we were when we took the 7-minute break. I just derived a very nice formula. I'm not happy with how aesthetically I wrote it, so I'm going to write it again nicely. Okay, this is the formula that we just written down, where this integral has some boundary conditions. Okay. This is the defining formula for the path integral formulation of quantum mechanics. Everything you can calculate from the Hamiltonian formalism that you already know and love, you can calculate from the path integral formalism that you have only just learned about, but which I'm sure you already love. And some things are easier in one formalism than the other. Okay. Now, again, this is an integral over all paths, where all the paths start at the point where you're beginning and they end at the point where you're stopping. So they start at QA and they go to QB. And in words, this is saying, figure out the action of each path and then sum over all the paths. And we give a very precise definition of the sum over paths. What it just says is break time up into discrete chunks and integrate the position independently over each discrete chunk. That is the meaning of sum over paths. It's a very concrete prescription which you can evaluate. Okay. I mean, you can evaluate it. It might turn out to be infinity, but that's just life. Okay. Now, now I should point out that often we don't want to just calculate the propagation amplitude. Maybe we want to calculate something a little bit different, like maybe an expectation value, right? So let me give you an example. What if you want to calculate something like this? I want to calculate this amplitude. I'm going to write down the formula, then explain what it means. This is a T2, it's a Q hat. T2 minus T1. God, my handwriting has really deteriorated over the last day. And again, a Q hat, and then e to the minus IH T1 QA. Okay. So this is, I start at QA, I go up to T1, then at T1, I insert an operator, Q hat. Then I go from T1 up to T2, and then at T2, I insert another operator, Q hat. Then I go all the way up to T, where I end at QB. Okay. This is what this is saying. It is basically computing the expectation value of two Qs in addition to this propagation amplitude. All right. Now, notice the way that I have set this up, saying I go to T1 first, then I go to T2. That means that capital T, my full time, is greater than T2, which is greater than T1, which is greater than 0. This is implicit in this formula. Okay. Okay. Now, what is this? I should be able to calculate what this is in the path integral formalism. Okay. And the answer, you can guess it. Okay. The point is, you should also, in doing the path integral, you should also multiply by the coordinate at each of these points, T1 and T2. In other words, this is equal to integral dq, q of T2, q of T2, q of T1, times the exponential of I times the s of q. Okay. This is the answer to that. Okay. So it's saying do the same path integral, but also multiply by q at T1, multiply by q of T2. All right. That is equal to this expression here. So this really, it should really make a lot of sense, right? Like, think about like sort of, normal probability or something like that. If you want to find an expectation value, you do an integral and you multiply by the thing you want to find the expectation value of, and that's what's happening here. Okay. This should seem quite reasonable. Now, I want to point out there's something subtle happening here. This Q appearing here in this formula is a number, right? I'm integrating over all paths. Q of T2 is a number, okay? And Q of T1 is also a number. I keep saying number, which I just mean this is literally the same thing as Q of T1, Q of T2. Instead of Q of T2, Q of T1, they're really the same because these are numbers, right? But on the other hand, on the left-hand side, these aren't numbers. These are quantum operators, Q hat. And so the ordering of these quantum operators matters. So notice that there is no ordering here, but there is an ordering on the left-hand side. So how does the left-hand side figure out what the order is? It does that because the construction of setting up this formula requires that T2 is greater than T1. In other words, it requires that the operators are time ordered. So what that means is path integral expectation values are always time ordered. Okay. So you have encountered the time ordering already in your life in the interaction picture of quantum field theory, which you all know already. This is another place where it comes up. If you're trying to do a path integral, then you will always get a time-ordered expectation value. I say always. There are ways to get the other ones, but they're very tricky and I mean, they're not completely simple. You won't get them in a simple manner. Okay. It's called the Schwinger-Keldysh formalism. We're not going to discuss that. The normal expectation value is always time order. Okay. So just to emphasize that, here's how we can write this. If we have two coordinates, t and t prime, then the thing that we get out from this is always going to be the time order expectation value of q of t prime. Just remember that because we're going to calculate something soon. It's important that it'll be time ordered. Okay. And by the way, I've quietly moved to the Heisenberg picture of quantum mechanics because I assume that q hat depends on t. Q hat of t is q with the e to the ih on each side of it. That's what q of t means. Okay. Okay, good. And now there's one more thing that we need to understand before we get into quantum field theory path integrals. Okay. And that is how to get the vacuum. Okay. So what do I mean by getting the vacuum? this is telling us how to go from QA to QB. But, in quantum field theory, we normally don't actually care about specific states that aren't the vacuum. The vacuum is the best state. Okay. So how do we get the vacuum zero from the path integral? All right. So let me define the vacuum carefully. I'm going to define the vacuum to be the state that when the Hamiltonian acts on it, it gives me zero. All right. And let me also define all the other energy eigenstates. So I'm going to call them n. And these guys are basically defined in this way. They all have an energy times n, so the other states, okay? Now, I want to now calculate a formula that replaces these QAs with the vacuum, okay? So how do I do that? So first, let me note that by the completeness of the spectrum, in other words, just by common sense, you can always write QA as a sum over the energy eigenstates. Okay, so here this is a position eigenstate. And here this is a sum over the energy eigenstates. You have to figure out what these CNs are for your given Q, but there always exists a set of CN, so this can be written. Okay. So now let me imagine doing the following thing. Let me take this and act on both sides of this formula with e to the minus I h hat t 1 minus I epsilon. Epsilon is a small positive number, which is unrelated to the previous epsilon. I'm sorry, I realized just now I should have given this a different name, but it's not related to the epsilon of the previous part. Okay. So if I act on both sides of this with this object, e to the minus I h hat t 1 minus I epsilon, sum over n, cnn, then what happens? Okay, so what am I doing? What I'm doing is I'm evolving in a slightly imaginary time, okay? This 1 minus I epsilon takes my real time and makes it a little bit imaginary, okay? This is meant to be the imaginariness of the time. And so it's a little bit of a Wick rotation, okay? But what does it do? Well, these are all energy eigenstates, right? So it becomes sum over n, Cn times e to the minus I n t minus epsilon times t en times n. Okay. So notice this part is an e to the I. So this part is oscillating. This part is minus epsilon. So this part is not oscillating. In fact, the bigger and bigger and bigger that I make t, the smaller and smaller and smaller this thing becomes, right? Because it's e to the minus a positive number, right? Now, in fact, let's now take the limit as t goes to infinity of this expression. If I do that, then what happens? This thing is an exponential suppression that kills all of the states except for the ground state. Because the vacuum state, the ground state, has E naught equal to 0, so it doesn't have that term at all. So if I take t goes to infinity there, every single state here dies except for the ground state, except for the vacuum state. Okay. So the vacuum or the ground state is the same thing, survives. And every other state goes away. So in other words, it is really easy to get the ground state. All you should do is evolve in slightly imaginary time. Okay. So now we have a simple formula for example, this thing here, this vacuum amplitude. Okay. What I should do is take t goes to infinity in this object with a small, sorry, I mixed up QA and QB here, with a small imaginary part. Okay. And then if you do that, then if you take t to infinity, it kills everything but the ground states. You just have 0, 0 left over here. Okay. So for example, if we now want to calculate, oh, sorry, I messed up one thing. This is not really equals to, this is actually proportional to that because of this C naught factor here that we can't really figure out usually. All right. But it's proportional to that. And so this now gives us some sort of useful formula. So let me now write down a useful formula. Imagine you want to calculate the time-ordered expectation value of q hat t1, q hat t2 between the vacuum and the vacuum. What do? You do a path integral. All right. Sorry, let me write this like this. On both the top and the bottom, you take t goes to infinity, but remember to multiply it by this 1 minus I epsilon. And you do a path integral. In the numerator, you do q of t1, q of t2 times e to the is of q. Okay. But this includes some imaginary time. And in the denominator, you do the same thing. But you don't put the q of t1, q of t2. Okay. And this is how you calculate this time-ordered expectation value in the vacuum. Let's just repeat how all the ingredients work. Because I'm doing q hat of t1, q hat of t2, I have q of t1, q of t2 in the numerator. Okay. Because I want to do the vacuum, I have this slight imaginary time here, this little wick rotation here. Okay. And because I don't really know what this factor C naught is, I divide by something here, which cancels everything except what I want. All right. There was a question here. If this is infinite, how do you calculate anything with it? This is how. Just divide by the thing, and all the infinities in this formula cancel out, and you just get exactly what you want left over. That is how to actually figure things out from path integrals. Divide by something which gets rid of the infinities that you want, that you don't want. Okay. Okay. Now, we are getting close to doing path integrals for quantum field theory. But before we do that, we need to develop a little bit of math, okay? So when I say math, I just mean, I'm going to say this a bit, I just mean we're going to need to take what's called a functional derivative. Let me just remind you what we just learned. We just learned how to integrate over functions, right? Oops. We just learned how to integrate over functions, dq. But now we might also want to differentiate with respect to functions. In fact, we should have learned that first, right? Normally you learn how to differentiate, then you learn how to integrate. So how do we differentiate with respect to a function? So often in physics, you will find yourself wanting to do something like differentiate with respect to a function. You don't know how to do it. It is very helpful to imagine discretizing whatever you're trying to do and then make it into a finite dimensional problem and then take everything to infinity afterwards. So let me give you an example of what I mean. Let's take a normal derivative first. So imagine that I have a vector xi in Rn, okay? The definition of the vector is, the partial derivative vector is that if you differentiate xi with respect to xj, that derivative is 0 if I is not equal to j, all right? And it's 1 if I is equal to j. So this is basically the basic formula of partial derivatives, right? It just says take partial xi, partial xj, you get delta ij. Truth is, with this formula, you can, really, basically this formula is all you need to take an arbitrary derivative of something. So now let's do functions. I want to differentiate with respect to a function. How would I do it? Well, let's just follow our nose. So for example, if I have q of t and I want to differentiate it with respect to q of t prime, what is it that should replace this delta ij over here? Well, probably going to be a delta function, right? Delta of t minus t prime. This is the definition of a functional derivative. Okay, so this defines this notation of partial q of t. And this is really useful, this thing over here. You can sort of see this is the fancy functional version of delta ij. If you discretize time and then sort of work out what it should be based on the discrete version, then you can derive this formula. Okay, but it's really just a common sense formula, I think. So let me give you an example of what this is good for. All right. So for example, this is the kind of integral we're going to have over and over again. Let me take delta j of t of the exponential of the integral dt prime j of t prime q of t prime. Okay. So I want to compute this functional derivative. Okay, so how do I do it? Well, I'm just going to apply all the rules of differentiation. So first I have an exponential of something. So by the rules of differentiating exponentials, it seems that I should just differentiate the thing in the exponent, which is this dt prime, j of t prime, q of t prime, times e to the dt prime, j of t prime, q of t prime. So this from here to here is just by the rules of exponential differentiation. And now what do we have here? Well, this j of t is going to hit this j of t prime and give me a delta of t minus t prime from this rule that we have here. And then I have integrated dt prime left with a q of t prime. And then this integral of its delta function will just give me q of t. So this turns out to be just q of t times e to the integral dt prime, j of t prime, q of t prime. So what happened? Taking a derivative of this thing with respect to j of t brought down q of t. That's what happened with this differentiation. Okay. This result right here actually is going to be important in what follows. All right. So if this logic was a bit confusing to you, take a look at the lecture notes where I actually do a bunch more examples. I've been planning to do them in lectures, but I'm running a little bit behind time, so I will not do that. Okay. Okay. We're about to move into path integrals for quantum field theory. So we're going to go up in infiniteness. Are there any questions about this before we go on? So this is section 3 of my notes, path integrals for free quantum field theory. Any questions? I see there are a few. Good. So there's a question about getting the LSE reduction formula. I think that was about when I did the denominator business, probably. It's not really related, to be honest. The LSZ reduction formula is that's more that relating correlation functions to the inner products of in and out states. So it's a little bit different, I would say. There's something similar in that you have to let's see what's the connection. I wouldn't say there's a sharp connection. We can talk about it afterwards. Maybe there is one. Thank you. Any other questions before we keep going? I don't see any. Okay, good. So now, quantum field theory. You know what? It's really easy to do quantum field theory now, okay? Because we did all the hard work already. So all we need to do now is just do an integral over fields instead of particle paths. So let me remind you, let's do this for the free real scalar field. So remember, the free real scalar field has the following action. It's the degree of freedom is phi of x mu, which is phi of time and which is phi of t and xi. Okay. And what is the action? The action is integral d4x of a half delta phi squared minus m squared phi squared. This is the action of the real scalar field. Okay. And if we integrate by parts on this action, we can write this like this, d4x 1/2 minus phi d squared phi. No, I got it like this, sorry. This is an integration by parts. Okay. Okay. This is the free real scalar field. And now what I want to do is do path integrals for the quantum field. Okay. So the question is really, is it any different from what we did for quantum mechanics? Well, let's think about it. So let's build up towards quantum fields, but let's do it really fast. Okay. So what did we do? We did path integrals for one variable. Q. Okay. Now, I think everyone can imagine that we do path integrals for two variables. Q, let me call it Q sub A, where A runs over one from 1 to 2, right? Everyone's okay with that. Wait a second. Okay. Okay, so everyone's okay with 2. Now let's make it, instead of 2, let's make it n, where n is some finite number. Everyone is still okay with that, right? Path integrals for n variables. We'll have some path integral, but we'll just have some complicated action, which depends on n variables. Okay, is everyone okay with that? Okay, so now let's imagine that we have this A index, and let's just imagine that this A index runs over, take A to run over all the points in space. Okay, so A is an index that runs over some discretization of the points in space. Okay. So now this is looking a lot like a quantum, like a field, right? I mean, you have QA of T, but A runs over the points in space. So this is basically the same information of a field, phi T of Xi, right? Where this Xi, the point Xi we're talking about is given to us by which A we pick. So the information of the quantum of the field is really very similar to that of the quantum mechanical particle. And if we believe that, if we believe that this works, then we can immediately guess an answer for the path integral, right? So the path integral that we care about is basically just going to be the integral over all field configurations, okay, times the exponential of I s of phi, okay, where integral d phi now means integrate over all fields which depend on both space and on time. Okay, before they depended only on time, now they depend only on both on time and on space. Okay, I'm going to call this quantity z naught, z because it's basically like a partition function, and naught because it's a simple version of something that we're going to calculate in a second. Okay, this is how we do path integrals for quantum field theory. We use this formula, where S here is just the action of the quantum fields. Okay. Any questions about this before I keep going? You might be alarmed at calculating with this, but you'll see that calculating with it is actually pretty simple. Okay. All right. But now, before doing that, maybe I'll ask you, there's two questions which you might have, which is basically, why? Why would I do this? What's the point, right? We have a Hilbert space picture. We have a canonical quantization picture. We have this Hamiltonian that we like. Why would we build this path integral formalism? It looks very ill-behaved and so on. So there are two reasons. Okay, one of them is honest. Maybe the honest reason, I'll give the secret reason later. So first, the honest reason. And the honest reason is that the symmetries are manifest. What I mean by that in a second. So you see, for example, this action is Lorentz invariant, right? You've shown already this S answer is Lorentz invariant, okay? And everything here looks like it's Lorentz invariant, right? You do integral of S is Lorentz invariant, you integrate something Lorentz invariant, so everything looks Lorentz invariant. But in the canonical quantization picture, that wasn't true, right? You had to, in the canonical quantization, you had this H. How is H defined? I mean, H, you have to pick a time slice, you have to pick a T, you pick some choice of T, and then, if you boost T, then it becomes messed up and gets mixed up with X, and you might worry, is it really Lorentz invariant if you have to pick a time and quantize with that time? It turns out that it usually is, but you might have been nervous about this because all the symmetries are broken in the calculation. In the path integral way of doing calculations, all the symmetries are preserved at all steps in the calculation. This is good. This makes some things much simpler, okay? And this is one of the reasons why we do path integrals. Okay. And now the second reason is maybe it's a little bit sleazy, but I'll tell it to you because we're within friends here. The sleazy reason is that the path integral lets you be careless. You can be careless. And what I mean by that is, you see, the structure of the Hilbert space, the structure of the state space in quantum field theory can actually be quite complicated. So for example, when we get to gauge theory, or you've actually already studied the Maxwell action, the quantum theory of the Maxwell action, it's a bit complicated. There are some constraints in the gauge theory action because not all of the photon polarizations are physical. We'll discuss that tomorrow. And what that means is there are some subtle constraints in the Hilbert space, okay? Some states are redundant, some states are not redundant. And the path integral is a useful way to take care of that for you, okay? As long as you integrate over everything in the path integral, everything in the quantum theory will make sense. And it's sort of instructive to do the path integral derivation of, for example, gauge fields, and then go and try to do the canonical quantization and try to calculate a loop. And you'll see that it's really quite annoying. The path integral is really the right way to figure out systems that have constrained Hilbert spaces. So for example, gauge theories. Okay. Okay. So this is why we do path integrals. Now, before in the next 20 minutes, I show you how to calculate something from path integrals, I'll now take some questions. There have been a few. Let's see. There's a statement about how time-ordered expectation values look like Feynman propagators. Absolutely, that's where we're going with this. Excellent observation. And then the next question is, how about causality? In canonical quantization, when computing the propagator, we had to introduce antiparticle amplitudes to calculate particle amplitudes in the space-like cone. How does that translate here? So that's great. You see, because the action is Lorentz invariant, everything you calculate from it will be causal automatically. Okay. So what that means is an action that has particles will necessarily have the antiparticles that you need to make everything causal. All right. So this is going to happen automatically for us. The truth is that was also true in the Hamiltonian picture. You know, people say, you know, you say we had to introduce, but the truth is we had no choice, right? It was there in the action. Any Lorentz invariant action will always have particles and antiparticles. But you know, it's maybe a bit simpler in the path integral point of view. Well, it's borderline, to be honest. The calculation is kind of the same at the end in either way. So yeah. Other questions? Any other questions? Okay. So in the last 15, 20 minutes, I'm going to calculate something with this formula to show you that we can. All right. And let's do a computation. Following the suggestion in the chat, we're going to begin by computing the following two-point function. The time-ordered correlation function of phi of x1, phi of x2. Okay. So why are we calculating the time-ordered correlation function? Well, number one, you already know the Feynman propagator is important in quantum field theory, and so it's good for us to be able to calculate it, and that's why we're calculating it. However, number two, it's good that this is the one that we want to calculate, the time-ordered one, because it's very hard to calculate any other propagator from path integrals. So it's a good thing that we want this one. So let's go ahead and calculate it. All right. We have a formula for this. We derived it in the case of quantum mechanics, but we can use it here as well. So the correlation function is the following. Correlation function is the following. This is the formula that we want to use. Okay. So basically, there's something in the top with two powers of the field, which in our case is now phi instead of q. There's something in the bottom, which doesn't involve the field at all. The thing in the bottom is exactly what I call z naught. Okay. And the thing in the top looks like this. So there's a z naught in the bottom, and in the top, there's an integral d phi. Oh, sorry, I should have not called this x1 and x2. I'm calling it x and y in my notes. Okay. Phi of x, phi of y, times e to the is of phi. Okay. So this is what we're calculating. Okay. So now we're going to calculate this path integral. That's what we're going to do in the next 10 minutes or so. All right. So to do this, I want to define something. I'm going to define z of j. Z of j is defined as integral d phi, so the path integral, times the exponential of is of phi plus I integral d4x, j of x, phi of x. Okay. So this is a definition of some quantity. Let me just explain what this means. Z of j is a functional, okay? So j here, j is a function, j of x. It's an arbitrary function. And z of j takes that function, it does something to it, and it spits out a number. And that number is calculated in this way. Okay, we integrate over all fields, each the is of phi, you weight phi by j, and you get some number out. Okay, and that is z of j. It's a functional of the thing j. Okay. Okay, now why did I do this? Well, let's see. Notice that I introduced some technology of functional differentiation, which we can now use here. So I want to point out that this quantity here can be obtained from this in a very simple way. So integral d phi, phi of x, phi of y, is equal to minus I ddj of x minus I ddj of y times z of j evaluated at j equals to 0. Okay. So let's take a second and stare at what's happening here. Okay. So remember what functional derivatives do is if I use them on something in the exponent, we already saw, I'll just scroll up for a second. We saw that what they do is they bring down the thing that they're multiplying, right? They bring down the thing that they're multiplying. So if I take this z of j and I take one functional derivative here and one functional derivative here, what that will do is bring down a phi of x from here and a phi of y from here. And once I have a phi of x and a phi of y, then that's exactly what's happening over here. All right, that's exactly this thing here. Sorry, I left out the e to the is in this thing. Okay. So this guy brings down this phi of x, this guy brings down this phi of y, and then we set j equal to 0, so then this thing goes away after we take the derivatives. Okay. So in other words, what this is telling us is that we should calculate z of j, take two derivatives of this j with respect to j, two functional derivatives, and then we'll get the answer. Okay. So how do we calculate z of j? Well, let me remind you of a formula from roughly 1 hour, 40 minutes ago. So I want to calculate z of j. But way back here, remember we did this integral? We had an integral where we calculate a multi-dimensional Gaussian integral. Okay, it had some interesting pieces here. Let me actually write that again so I can modify it. Sorry for all the scrolling. So there's an integral that I wrote a while ago, which I'll just repeat it here now. Go dxi. Two plus I ji xi. So we did this integral and we calculated that this was equal to 2 pi to the n over 2 divided by root det a times exponential minus half ji a inverse ij jj. Okay. So this is from earlier. Okay, we calculated this thing. I put an extra factor of I here. That's useful for later. Okay, this I results in a minus sign here. It's not a big deal. Now, now what is the path integral we want to do? The path integral we want to do is integral d phi exponential of minus 1/2 phi. Sorry, try to get this right. Signs are actually important here. Of x, and then plus I j of x. Sorry, leave that I here. Okay. So now that we have these two things, we can stare at these two things together. What this is saying is, so let's just compare these two things, okay? Here we're integrating a finite dimensional variable with some quadratic piece here, some matrix A multiplying xi and xj, all right? And there's a linear piece here in j. And the answer is the inverse of the quadratic thing with 2 powers of the j, okay? This takes basically the same form, right? Because we're integrating over my field phi, and here's a phi of x and a phi of x. There's a quadratic piece here, which is like this quadratic piece here, except that the operator A is not a matrix really, it's a differential operator, but it's still a linear operator. It's basically the same idea, okay? So in fact, we can directly use this formula to calculate this, right? And the basic idea is that this is just an infinite dimensional Gaussian integral. That is the path integral of the free quantum fields. Okay. Okay, but let's just match everything now to try to use this formula. So this aij is replaced by this thing here, and there's an I. So what that means is that the thing that used to be A is now I times partial square plus m square. And the thing that used to be a vector j is now a function j, except for that it's basically the same. And so we can now immediately take over the formula. The formula is z of j is the determinant of this operator A. So remember, there was this det A here. So now det A is the operator partial square plus m square. There's a factor of minus 2 pi I, which honestly, I don't know why I'm even keeping it, but I'll explain it later. Minus 1/2 squared. And then this thing here is replaced by the exponential of minus 1/2 d4x d4y j of x times j of y times df of x and y. Okay. Now, why am I calling it df? df from this formula should be the inverse of this operator A. It turns out that df will end up being the Feynman propagator, but we don't technically know that yet. For now, df is just the inverse, is something like partial square plus m square inverse. So what that means is, let's write down what that means as an inverse. If it's an inverse, it means, oh, there's an I here. If there's an inverse, what that means is that if I act on df with the operator, I get the identity, which is now this delta function. Okay. So this is the definition of df. Okay. So here is my z of j for quantum field theory. This is an explicit calculation of z of j in quantum field theory. Okay. Now again, let us take a second to stare at this. I'm actually doing okay on time, so we can take more than a second to stare at this. There's a lot going on here, so let's unpack it slowly. There is the determinant of partial square plus m square. That might sort of stress you out a little bit. What is the determinant of partial square plus m square? So this is what's called a functional determinant. Okay, because it's again, it's a determinant of an infinite dimensional operator. And this is a functional determinant. And it's really quite beautiful. So in the homework, you will calculate this for a quantum mechanical example. To calculate it, what you do is, if you want to find the determinant, then what you should do is find all the eigenvalues and take the product over all the eigenvalues. That gives you the determinant. And that, of course, is the thing you can do for differential operators. You can find the eigenvalues and take the product. That's what the functional determinant is. This 2 pi I, notice that it's inside the determinant, which really means it's 2 pi I raised to the power of infinity. So this quantity here is actually extremely infinite, all right? And that's okay. We'll just live our life without it. You'll see it will not be a big deal, all right? Okay. And df is defined in this way. So now we're going to calculate df and see that it is the Feynman propagator that we know and we love. Okay. Are there any questions about this before I go on to finish the calculation? Oh, I see there are some. There's a question from, I guess, a few minutes ago. The question was, if it chooses all paths between 2 points, it does not obey Lagrangian because Lagrangian means the shortest path. That is correct. We integrate over all field configurations between 2 paths, not just those that satisfy the equations of motion. Okay, that is absolutely right. Classical physics says, find the shortest path, the lowest action. Says sum for all the paths. Okay. Questions. Is the question summarizing everything? I'll do. All right. So let me finish the calculation and then we'll stop. So I want to solve this equation. Okay, so I want to solve this for the Feynman propagator. All right. Does anyone have any ideas how we solve this? Tricks? This is a differential equation. How do I solve it? The answer for everything that involves a differential equation in a system with translational invariance like this one is to go to Fourier space. Okay. In other words, I assume that I can write df of x and y in this way. Integral d4p divided by 2 pi to the 4th times e to the minus ip x minus y df twiddle of p. So here I am integrating over a momentum p, okay, and I'm calculating df twiddle of p. Okay, df twiddle of p is the momentum space version of this object df of x and y. Okay, so now let's take this and stick this into here. Okay, so if we do that, then we imagine acting with this partial square on this guy. Each partial square brings down a p square. And what we find after a tiny bit of algebra is d4p over 2 pi to the 4th times minus p squared plus m squared e to the minus ip x minus y times df p twiddle of p equals to minus I delta 4 x minus y. Okay. And now we want this to be minus I delta to the delta 4th for the delta function of x minus y. That will happen if we are Fourier transforming a constant. At the moment, we're not Fourier transforming a constant because this is p squared plus m squared here. So we pick df to cancel that, which means that df twiddle of p is equal to I over p squared minus m squared. Okay. And this should look familiar to, this is the Feynman propagator from the earlier part of the course. And now let's just finish the calculation completely once and for all. We now have figured out what df of x and y is. df of x and y is the Fourier transform of I over p squared minus m squared. And now, going back what seems like a long distance, we know that what we want to do is take two functional derivatives of z of j to calculate this two-point function. If we take two functional derivatives of z of j, the first one will bring down j times df. The second one will get rid of the j. And so what we find at the end of the day, after all the dust settles, and you should all check this, of course, is that t of phi of x, phi of y, is equal to df of x and y, and df of x and y is equal to the integral d4p over 2 pi to the fourth I over p squared minus m squared e to the minus ip x minus y. And this is the Feynman propagator that you already know and love, which we have now rederived from path integrals. Okay. Okay. So I have 5 minutes to go. So first, before I summarize, are there any questions about this calculation? And then I'll summarize everything that we did today, which was really a lot of material in a very short time. Yeah. There are some requests about the video. Of course, we'll upload the video. Yeah, don't worry. Any questions?
Should I turn off the video?
Maybe not yet. I think I'll just ask if there's any technical questions, and then I will. Then I'll summarize maybe, and then we can stop the video. How about that? Okay. There are no technical questions. So let me just summarize everything that we did. Okay. Summary of today's lecture. Number one, the chance to go in any quantum system from some state 2 to evolve with any Hamiltonian from some state 1 is equal to the sum over all ways to go from 1 to 2 times e to the is. So this is a sum over all configurations, and each of them is weighted by e to the is. Okay. Now I say sum, this is more like an integral, but it's some complicated object that involves summing, integration, and so on. And the point is just that every way of going from 1 to 2, you figure out all of them, and you weight the action, you weight the answer by that exponential. Okay. Now, that's basically the point of today. And another thing that we did, which was done quite quickly, is that for the free quantum theory, this integral is Gaussian. So we can do it. I'll mention a little bit next time. If the integral is not Gaussian, we can't, but we can find a way to approximate it. And that way to approximate it is exactly the Feynman rules. Okay. And that's really the point, I think, just that you can write the answer in terms of a sort of path integral. And there are a lot of technical details about how to actually do these calculations and so on. But these details are mentioned in the lecture notes. You can take a look at them. The main thing I want you to take away from here is really just that there is a way to calculate all amplitudes in any quantum system by doing some sort of an integral over all the ways to go from one of them to the other. Okay, so that's the main point. And let me stop here and take questions. Yeah, so we can maybe turn off the video now.